Okay, so we've seen one downside of Quicksort, and that's the following. We say that Quicksort, as we've implemented it, is not stable. So a sort, but merge sort is actually. Okay, so for a sort to be stable, if we sort in one order A and then another order B, then within ties of order B, the elements should still be sorted with respect to order A. And we do not have that property for Quicksort. Okay, so that's one downside. Fortunately, I have some more bad news for you about Quicksort. Okay, well, let's. The positive thing about Quicksort is it's in place, right? We don't need to have this auxiliary array. So if you're sorting millions of elements, you don't need to have 2 copies of an array of millions of elements. Okay, so that's good. So it's not all bad. But there is some bad stuff. So let's think about what happens when we try to do Quicksort on an array that's already sorted. Shouldn't that be quick, right? So if I have an array like 1, 2, 3, 4, 5, 6, 7, 8. So the pivot's always going to be the last one. Okay, so I'm saying put everything to the left of the pivot that's less than it, and everything to the right of the pivot that's greater than it. Well, there's nothing greater than it. So what that means is the first split, I'm going to sort this, and I'm going to sort this. Well, this is really quick. But that's not so quick. Okay, so to sort this, then we're going to take the right most element, that's the pivot, which means next, recursively, we're going to sort this chunk and this chunk. Okay, and you can see where this is going. If the array is sorted, I'm never actually, when I try to do this divide step, where I divide the array into smaller parts, I'm not actually going to divide it very evenly. So it takes, just like with merge sort, I have to loop through the entire range. So every step takes time proportional to the number of elements in that range. So what this means is it's going to take n steps, and then this is going to take n minus 1 steps, this is going to take n minus 2 steps. So the complexity, so dot dot dot, the complexity of Quicksort, put it in quotes, on an array that is already sorted, when we choose the pivot as the rightmost element, is n plus n minus 1 plus n minus 2 dot, 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 down to 1 roughly, which is O of n squared. Okay, for a similar reason to why insertion sort was O of n squared. Okay, that's not good. So we actually found that the worst case time complexity of Quicksort is the same as insertion sort. It's O of n squared. Okay. So therefore, we have that. Now it turns out that the best case, well, it depends on how you implement it, but the best case and the average case are O of n log n. So in practice, it's still fine, and there are ways to choose a better pivot, so that you're not always choosing the last element, but sometimes what you can do is you can look at the last element, the first element, and then the element in the middle, and choose the median between them. So you're trying to split if you can split the list perfectly in half, then you'll get the same kind of recurrence that we had with the merge sort, where we kept splitting into equal halves, and we did that log n times. Here we can't, if we're not able to split it into equal halves, we have to go, it takes n times until we get down to an array of size 1, so that's not going to be any good. So our goal, so for a better implementation, we're still going to have a worst case of n squared, but for a better implementation, we can choose pivots that are less likely, or let me say it, we can choose pivots that are more likely to split our halves evenly. And you can read up on this. It's pretty interesting, but the code is a little more complicated, so I don't really want to get into it right now. All right, so that's the good, the bad, and the ugly of Quicksort. So it's not a stable sort, and the worst case time complexity is not very good. But the average case time complexity is good, and we don't have to have this extra auxiliary array that we copy things into. So that's nice. Okay. But the question I have now is, it seems like we're running up against this n log n. So can we do any better than that? And I want to present an argument in the next video about that, and we'll continue the discussion in class. Okay.